Hello my friends, and welcome back to the You Can Do TV channel. Today we will visit Norway, where we will explore the construction process of the largest transport project in Norwegian history, the E39 coastal highway route. In the next parts of the video, we will directly visit the construction sites of the mountain tunnel and suspension bridge. The construction of the E39 coastal highway route is a massive undertaking and the largest transport project in Norwegian history. The project aims to connect the entire western region of Norway with an improved and continuous highway route without the need for ferries. Spanning a length of 1,100 kilometers and passing through 6 counties, the current route includes 7 ferry connections. However, the new highway will eliminate the need for these ferries, significantly reducing travel time from around 21 hours to approximately 11 hours. The construction plans for the E39 coastal highway route involve several challenging sections. For instance, the section north of Stavanger includes the first project, known as the E39 Rogfast. This project will bring the towns of Stavanger and Haugesund closer together by crossing the Bonafjorden via a subsea road tunnel. The tunnel's lowest point will be approximately 390 meters below sea level, ensuring safety through emergency exits, emergency lay-bys with telephones, and camera surveillance. Another complex section lies between Bergen and Ålesund, where the route encounters the Sandfjorden. One possible solution for crossing this wide and deep fjord is an end-anchored floating bridge. This bridge would be anchored on land on both sides and span the fjord, which is almost 400 meters deep. Alternatively, a multi-span suspension bridge with towers anchored to the seabed and near land on both sides, or a submerged floating tube bridge suspended in mid-water, are also being considered. The construction process for the section between Ålesund and Molde, which encompasses a 16-kilometer subsea tunnel and a 2-kilometer suspension bridge. The construction project begins with thorough geological and geotechnical surveys of the seabed and surrounding areas to gather essential data for the design and engineering of the tunnel and bridge structures. The tunnel boring machines are used to excavate through the seabed and create the tunnel. In addition to the main tunnel, emergency exits are strategically placed along the tunnel's length to ensure safety. These emergency exits serve as access points in case of emergencies, allowing for evacuation if needed. To enhance safety and security, emergency lay-bys equipped with emergency telephones and camera surveillance systems are established within the tunnel. Simultaneously, the construction of the suspension bridge takes place. The suspension bridge is designed to span a specific section of the fjord, connecting the two land masses. The construction process entails the erection of towers on both sides of the fjord, serving as anchor points for the suspension cables. The suspension cables are carefully installed and tensioned to support the weight of the bridge deck. The Selva Tunnel was constructed to connect two regions separated by a daunting mountain range. Over the course of 9 years, the construction crews employed a range of innovative techniques to tackle the rugged terrain. The initial phase involved extensive excavation work, as heavy machinery and skilled operators worked tirelessly to remove vast quantities of rock and earth. Blasting techniques were utilized strategically to break through the toughest sections, creating a pathway for the tunnel. Once the excavation was complete, the construction teams focused on reinforcing the tunnel structure. Steel supports and concrete were meticulously installed to ensure the tunnel's stability and safety. Advanced engineering principles were applied to guarantee that the tunnel could withstand external pressures and potential geological disturbances. In this step, workers using drilling machines to bore holes into the cliff or rock face. These holes are typically 6 to 10 meters deep, depending on the specific requirements of the project. Once the holes are drilled, explosives are carefully placed inside them. The type and amount of explosives used are determined by the geological conditions and the desired effect. Controlled explosives, such as dynamite or similar materials, are commonly employed. The explosives are carefully positioned and secured within the drilled holes, ensuring proper distribution and control. After the explosives are securely in place, they are detonated in a controlled manner. The detonation triggers a controlled explosion that fractures the rock mass, breaking it into smaller, more manageable pieces. This process is crucial for loosening the rock and facilitating its subsequent removal. Following the detonation, excavators, trucks, and specialized machinery come into play. Excavators are used to remove the fragmented rock and debris from the blast site. Trucks transport the excavated material away from the tunnel area to designated disposal. The Gubrist Tunnel, located north of Zurich in Switzerland, is a crucial infrastructure project responsible for alleviating traffic congestion on Swiss highways. As part of the expansion project, the construction company Marti Group was tasked with paving the roadway in the third tube of the tunnel, which posed a significant engineering challenge. Before the roadway paving process could begin, various preparatory steps were undertaken. The tunnel, stretching 3 kilometers in length and consisting of 2 lanes, had its embankments completed, and the sides were filled with excavated material. Once the berms were established, the tunnel was ready for the installation of the road surface. The roadway comprised 2 layers of gravel, namely the formation layer and the fine planing layer, followed by 4 asphalt layers. These layers included an 8 cm thick base layer, an 8 cm thick binder layer, and a 3 cm thick wearing course layer. The process began with the application of 2 gravel layers, namely the formation layer and the fine planing layer, which served as the foundation for the asphalt pavement. These layers were carefully leveled to ensure a stable base for the subsequent asphalt layers. Following the preparation of the foundation, 4 asphalt layers were installed: an 8 cm thick base layer, an 8 cm thick binder layer, and a 3 cm thick wearing course. Maintaining the highest quality standards was of utmost importance during the asphalt paving process. The Marti Group utilized their own material feeder, ensuring a consistent supply of asphalt and precise distribution. Additionally, the construction team relied on a 3D model of the roadway, which allowed for accurate measurements and precise placement of the asphalt layers. This advanced technology enabled the team to achieve a remarkable level of precision, with an installation accuracy of up to 25 centimeters. To ensure the longevity and durability of the asphalt pavement, thorough compaction and consolidation were essential. Following the asphalt placement, the layers were subjected to compaction tests to ensure that they met or exceeded the required standards. The results of these tests demonstrated that the compaction levels were on average 30% higher than the specified requirements, indicating a high-quality pavement. The asphalt paving process involved the use of specialized equipment, including an asphalt feeder and an asphalt paver. The feeder, with a capacity of 45 tons, efficiently supplied the asphalt to the paver, preventing interruptions in the paving process. The paver, equipped with infrared sensors and an automated leveling system, ensured precise and uniform application of the asphalt. The paving machine moved along the tunnel, maintaining a consistent depth and alignment, while the sensors continuously monitored the height and adjusted the paving screed accordingly. Throughout the process, key parameters and progress were continuously monitored to ensure adherence to the pre-programmed construction schedule and maintain high-quality standards. The asphalt paver recorded vital data, such as the distance covered, the amount of asphalt used, and the surface temperature of the newly laid layers. This information allowed the construction team to track progress, identify potential issues, and make necessary adjustments promptly. The asphalt paving process spans several nights to minimize disruptions to traffic flow. Each night, approximately 250 to 300 tons of asphalt were laid, covering a distance of around 120 meters. The sequencing and logistics of asphalt delivery were meticulously planned to ensure a seamless operation. Real-time communication and coordination between the asphalt production plant and the construction site facilitated timely deliveries, minimizing delays and optimizing construction efficiency. Quality control remained a top priority during the entire asphalt paving process. The temperature of the asphalt was closely monitored to ensure optimal compaction and bonding. Infrared cameras captured the surface temperature of the asphalt, providing valuable data for quality assessment. Additionally, manual temperature measurements were conducted at regular intervals to validate the results obtained from the infrared cameras. As the final layer, the wearing course, was installed, the asphalt paving process in the third tube of the Gubrist Tunnel neared completion. The Hardanger Bridge is a magnificent suspension bridge located in Norway that spans the Hardanger Fjord, connecting the municipalities of Ullensvang and Ulvik. Completed in 2013, it is one of the longest suspension bridges in the world, measuring approximately 1,310 meters in length. The bridge was designed to withstand the harsh Norwegian climate and provides a vital transportation link in the region, significantly reducing travel time between the two municipalities. The construction process of the Hardanger Bridge began with blasting work. Tunnel engineers made a breakthrough by the fjord in Valovik, which soon became a new landmark in Hardanger. The construction of the bridge foundations and bridge pylons for the Hardanger Bridge was a meticulous and time-consuming process that spanned several years. It involved various stages and techniques to ensure the stability, strength, and precision of these critical components. The construction journey began with the excavation of the ground to prepare the foundation sites. This process involved removing soil and rocks to create a solid base for the bridge. The excavation work was carefully executed, considering the geological conditions and engineering requirements of the area. Simultaneously, the construction team embarked on pouring the concrete for the bridge pylons. This marked a significant milestone in the construction process, as the pylons serve as the towering support structures for the bridge. Pouring the concrete required careful planning and execution. Each pylon's foundation consisted of a substantial amount of reinforcement and concrete, ensuring its stability and longevity. Once the foundation work was completed, the construction of the bridge pylons commenced. The pylons were built using a climbing formwork system, which allowed them to be erected in manageable sections. This method ensured that the construction process was carried out with precision and accuracy, as each section was aligned and securely attached to the previous one. Over time, the pylons gradually reached their towering heights, becoming an impressive and prominent feature of the bridge's landscape. The construction team dedicated themselves to ensuring that each pylon was built to the highest standards of quality and safety. Both bridge pylons had reached their full height, and the formwork was removed. The pylons towered 202.5 meters above the fjord, with the top walls measuring 12 meters high. The cable spinning process began in November 2011. Spanning a length of approximately 1,310 meters, the bridge required strong and durable cables to support its structure. The cable spinning process commenced in November 2011 and played a significant role in ensuring the bridge's stability. The spinning wheel, a specialized machine, was used to carry 4 bundles of galvanized steel wires across the bridge span. The spinning wheel traveled from one end of the bridge to the other, attaching 8 wires to the existing strands on each trip. This process was repeated until all the required wires were in place. The steel wires used for the cables had a diameter of 5.3 millimeters, and each cable consisted of 19 strands, with each strand comprising 528 individual wires. The cables were fixed to the strand shoe, located in the anchorage block at the bottom of the splay chamber on each side of the fjord. The strand shoe played a crucial role in anchoring the cables and providing stability to the bridge. With meticulous precision, the cable wires were attached to the strand shoe, ensuring a secure connection. The cable spinning process posed several challenges, particularly due to the extreme weather conditions. The construction site experienced storms and strong winds, especially during the winter season. The adverse weather conditions sometimes caused delays and added technical difficulties to the cable spinning process. Notably, on Christmas Day 2011, the bridge was hit by a severe storm named Dagmar, which further complicated the cable spinning work. Despite the challenges, the dedicated construction team persevered, working diligently to complete the cable spinning. The process required precision and attention to detail to ensure the cables were properly installed and aligned. The cables were an essential component of the bridge's structural integrity, providing the necessary support to withstand the forces acting upon it. After approximately 9 months, the cable spinning process was successfully completed on the 18th of July 2012. The completion marked a significant milestone in the construction of the Hardanger Bridge. The steel wires were securely in place, providing the bridge with the strength and stability needed for safe passage. The construction of the steel box girder sections was a vital aspect of building the Hardanger Bridge. These sections formed the main structural elements of the bridge, providing support and stability to the overall bridge structure. The construction process involved several stages, from fabrication to assembly and installation. Fabrication of the steel box girder sections began at the fabrication yard. Large steel plates were first cut according to precise measurements and specifications. These plates were then shaped and bent using specialized machinery to form the required curved and tapered sections of the box girders. Welding was performed to join the plates together, creating the hollow box-like structure. The assembly of the steel box girder sections for the Hardanger Bridge was a critical phase in its construction. The girder sections, weighing a total of 7,850 tons, were built abroad and transported to the construction site in Hardanger in September 2012. Upon arrival, the hoisting and installation process commenced. Specialized cranes were employed to carefully lift the steel box girder sections into position. The sections were then attached to the hangers, which had been previously installed, and securely bolted to the girder already in place. The hoisting and installation of the girder sections required precise planning and coordination. Each section had to be positioned correctly to ensure proper alignment and fit. Skilled workers, including riggers and crane operators, worked together to execute this process with utmost care and precision. During the installation, temporary supports were strategically placed to hold the sections steady, minimizing any potential movement or misalignment. This allowed the workers to accurately position the steel box girder sections and make the necessary connections. Once in position, the sections were bolted to the existing girder. The bolts used were specifically designed to provide strong connections and ensure the stability and integrity of the bridge structure. Rigorous quality control measures were implemented to ensure the correct torque and tension of the bolts, guaranteeing the reliability of the connections. The assembly of the steel box girder sections was a complex task that demanded meticulous attention to detail. It required the expertise of skilled professionals, including engineers, welders, riggers, and crane operators, who worked collaboratively to complete the installation process. The successful assembly of the steel box girder sections marked a significant milestone in the construction of the Hardanger Bridge. It brought together the individual components to form the bridge's superstructure, providing the necessary strength and load-bearing capacity. The careful planning, precise positioning, and secure bolting of the girder sections ensured the structural integrity of the bridge. This phase of construction showcased the expertise and dedication of the construction team, bringing the Hardanger Bridge one step closer to its completion. In the next part of the video, we will have a driving journey across this bridge. Let's see and discover it. The Hardanger Bridge, located in western Norway, is a magnificent feat of engineering that stands as one of the country's most remarkable structures. Spanning across the scenic Hardanger Fjord, this awe-inspiring bridge connects the municipalities of Ulvik and Ullensvang, providing a vital link between the eastern and western parts of Norway. With its impressive design and breathtaking surroundings, a trip across the Hardanger Bridge offers a truly memorable experience for locals and tourists alike. The Hardanger Bridge, completed in 2013, spans an impressive distance of 1,380 meters, 4,528 feet, making it one of the longest suspension bridges in Europe. Its construction was a complex and meticulous process that took several years to complete. Engineers and workers faced numerous challenges, including the need to design a structure that could withstand the region's harsh weather conditions and the immense forces exerted by the fjord below. The bridge's design showcases a striking blend of functionality and aesthetics. Slender towers rise majestically from the water, supporting the suspended roadway with an intricate system of cables. These cables are precisely tensioned to distribute the weight of the bridge evenly, ensuring its stability and strength. The result is a visually stunning structure that harmonizes with the surrounding natural beauty. During the construction phase, engineers employed advanced techniques and materials to ensure the bridge's durability and longevity. High-strength steel and concrete were used to withstand the corrosive effects of the saltwater environment. Stringent quality control measures were implemented to guarantee the integrity of the construction and ensure that it adhered to strict safety standards.